by summing over every possible intermediate position. And obviously that's continuous, so it would be actually an integral, loosely summing. Okay, so that's the kind of conceptual step that rather than just taking some finite number of these little gaps, you can really extend it, and you don't have anything left in the middle there. So this is the amplitude with no screen at all. Then I can think of some fictitious screen which lets everything through, but I can still think of considering all the different points on that and summing over them all. And so we're nearly there at the path integral. What the path integral is to say, well, let's not take one of these screens, let's take lots of these screens all the way in between here. And so if I sketch that, then you'll see that we end up summing over all possible paths. So the next step is many screens. So what do I do there? I just simply put in as many as I want. So then the particle has to go through here, 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 for example, and off to this point, or it could go through that, could go through anyway. I mean, obviously I can't draw them all. There's lots of different possibilities. So basically you just link up all these things like that. So you get all these different paths. So these are all separate different paths. Probably not very clear, but you get the idea. The first passes through the first screen, so it's got different choices there, and then it's got all possible choices for the next one and all possible choices for the next one. So we take the limit where there's screens everywhere in between here. And each one's got an infinite number of slits. Then we're going to sum over all possible paths, because that's basically what you're doing. You're saying it follows any given trajectory, because at any point in that trajectory is passing through one of these screens, and so on. So, around to where I started. Okay, just to formalize, well, not really to formalize it yet, but just to say roughly what the idea. In other words, the amplitude from Qi to Qf sum over all paths Q of t, amplitude for Qi to Qf along a particular path. So you can if you take a specific path, you could calculate some amplitude for that, and then what you do to get the general amplitude that just for starting here and finishing here, well, in the given time and other things I've not written down here, then you pick amplitude for a specific path and you sum over all possible paths. Now, how do you sum over all possible paths? Well, that's what we're going to see next, how you actually do that. But conceptually, this is the idea of path integrals, that you can't specify a path. If you only know where the particle starts and where it finishes, then you get the total amplitude by summing over all possible paths in between. Okay, so what we do now then is just give a definition of the path integral. And, well, it's essentially, it's sort of going back to this idea of these several screens in here. So rather than having screens at some position in some other coordinate, we'll think of, after small intervals of time, we'll see where the particle is and some overall possibilities. So rather than thinking of this two-dimensional picture here, I think of, say, time as going along this way and my position as going up that way. And each small interval of time ask where's the particle and some overall possible positions of the particle. But it's a way of just defining what this some overall paths actually is. Okay. So so we don't really need this. So let me use the center board since it's probably clearer to see. Okay, so this is definition of path integral. Okay, so this is rather messy, but it's something that it looks difficult at first, but you'll see that it's something that's reasonably well defined. And there's two ways that we could go. One is we could just say, starting from this definition up here, the point was, great, I just rubbed it out, I needed an amplitude for the particle to go from this initial point to this final point along some specific path. Now, how do I work that amplitude out? Well, I don't really know how to work that amplitude out instantly. So what I could do is I could just propose some form for that amplitude. So one method is I could just say, well, let's take something for that amplitude, and one thing you could do is say, let's take that amplitude to be exponential of I times the action, classical action, for the particle to take that path. Now, that would be one way to do it, and if you hadn't known any quantum mechanics before, I could just postulate that, and then we could go on and see why that made sense, how we could compare to classical mechanics, and so on. But since most of you have seen quantum mechanics before, then I've also said that this thing here is the way to write that amplitude in terms of the Hamiltonian. So what we'll do is we'll instead work from what you know and show that if we work from what you know, you do in fact get back to what I've just said, that the amplitude for a specific path is given by e to the I over h bar times the classical action along that path. Okay, so how do we do it? Well, we're going to start from this, obviously. Now, if you like, it's a bit like integrating. We've got some whole interval of time. Don't really know how to evaluate that exactly, so let's split it up into small bits and evaluate it approximately, just like you would integrate a general function by splitting it up into small segments and pretending that the area under the graph for each segment was just a rectangle. So it's the same sort of idea. So we split time into intervals of length delta t. So it's a total time over some integer capital N. And then we just write this thing out. So if we split it up, then of course, because of the properties of the exponential, we just split that up into lots of products of exponentials. So okay, so that's my e to the minus I over h bar h at t, and we're splitting my time into n intervals of length delta t, then this just becomes n products. Delta t, and then another one, and so on. So the product of total of n of these things, capital N. Okay, so squeezing it in there, and we end up then with qi. So there's n bits there. Okay, Now, how does that help us? Well, we're going to use our trick again of inserting this complete set of states or putting in the identity operator and using the spectral representation. So what I'm going to do is everywhere between two of these products stick in an identity operator in this form. I'm going to put it there, in here, and so on. Sorry, don't need it there. Okay, so that's on the right and the left of each of these exponentials, there's a position eigenstate. Okay, and of course, each time I'll label the integration over some different variables. I'll label these as Q1 up to Qn minus 1. So what does that give us in total? Well, it's looking a bit messy, but okay, so there's n minus 1 because there's n products of the exponential, and we're just putting the gaps in between. And then what we have here then, we have Qf e to the minus I over h bar h hat delta t Q n minus 1. Okay, so we've got something in there, call that with Q n minus 1. And then we've got various products. The general one is Q, let's call it j plus 1 e to the minus I over h bar h hat delta t Qj. Okay, so they're all of the same form, these things, so just you can write in as many as you need. Okay, so it's just lots of products of exactly the same form. And of course, it's the same form as what it started with, except that this delta t now is a very small time. So we're going to use some approximation when we do that. Okay, so we're just putting in this. We've got the integrals. You see the integrals over all the intermediate positions. So Q1 is just the position. So it starts at position Qi at time 0. At time delta t, then it's at position Q1, but we sum over all possible positions at Q1. Then it moves on to position Q2 at time 2 delta t, and we sum over all these possible positions and so on, until finally ends up nearly at the end of the time interval it's summing over all these possible positions, and then it has to finally end at our given position Qf. So that's all it is. And that's basically, we're going to take a limit delta t to 0 or n to infinity, and that gives us a sum over all the paths. Okay, so is that okay? Is everyone happy enough with that? So you're going to think as n goes to infinity or delta t goes to 0, get sum over all paths. Okay, so let's see. So I'm hoping we can finish this off. 15 minutes should be okay. So I just want to evaluate, so all these factors in here, so each bit like this is some inner product, and it's some number, and then we multiply all these together. So what I want to do is evaluate this thing here, and because we're taking delta t to 0, I just need to evaluate it approximately for small delta t. And then we put it all together and take the limit, and we get the exact answer. So as I say, it's exactly like when you integrate a function. You've got an arbitrary shape of the function, you split it up into lots of segments, and you pretend each one's a rectangle, which is approximately true if you've got a very narrow band. Not exactly true, but it's good enough to define what you mean by an integral. So this is the same idea here. And I'll not go into too much detail of exactly how the approximation works, but we'll just sketch it. So let's calculate an arbitrary one, so q j plus 1 for